Well, good afternoon, everyone. My name is Bruce Baer. I'm Dean of the College of Forest Resources, and it's my pleasure to welcome all of you to the 16th Denman Forestry Issues series entitled Bioenergy and Biofuels in Washington. I look forward to this session this afternoon, as I hope all of you do, as it's a very timely set of topics that we're going to hear about today. Basically, the theme will be, how do we convert the agricultural, the forest, and the municipal waste biomass into a variety of bioproducts? This subject is in keeping with the purpose of the Denman Forestry Issues series, which is to provide information and discussion on timely forestry and natural resource issues. And as with all activities associated with an academic setting, our ultimate goal is to inform and educate our students, our faculty and staff, as well as resource professionals, citizens group, landowners, and the general public. These programs are made possible through the generous support provided by the Denman Endowment for Student Excellence in Forest Resources, and they support the college's vision of world-class and international recognition as a source of knowledge relevant to environmental and natural resource issues. Before I go any further, I would also like to acknowledge two people who have helped put this program together. First, Ellen Matheny, Educational Outreach Specialist with the University of Washington's Olympic Natural Resources Center in Forks, who basically took care of all the arrangements for this session today. And secondly, Bob Edmonds, our Associate Dean in the College of Forest Resources, who organized the program. The mission of the College of Forest Resources is to study and investigate the functionality and the sustainability of natural resource systems in both natural and managed environments, using an interdisciplinary approach across multiple spatial and temporal scales to include our urban, suburban, and wildland landscapes. In our college, we focus on programs in sustainable forestry, sustainable urban ecosystems, and sustainable forest enterprises. Sustainability serves as the goal for all of our programs and includes all resources such as timber, plants, water, wildlife, or insects, for example, considers the needs of future generations as well as those of the present, and strives for a dynamic equilibrium that balances ecological functions and conditions with social and economic factors. Today, we wish to focus on a variety of issues related to the conversion of biomass to bioenergy, biofuels, or other bioproducts here in Washington State. And we believe that this theme does, in fact, reinforce the college's theme of sustainability. There's many types of biofuels that you'll hear about. I'm just going to list a couple. One is biogas, sometimes called swamp gas, landfill gas, or digester gas, produced under anaerobic conditions from organic waste and is composed of methane and carbon dioxide. Second is bioethanol, produced by fermentation from a variety of crops, typically sugarcane, corn, sugar beets, potatoes, and many others. And then there's additional biofuels, such as cellulosic bioethanol, which is made from lignocellulose, which would be materials such as corn stover, wood chips, switchgrass, wheat straw, etc., using one of two processes, either a biological approach, cellulosis, or a thermochemical approach, gasification or pyrolysis. And then there's many others: biodiesel, bio-oil, butanol, biomethanol, propanol, and many others. Why are we interested in bioenergy and biofuels? Well, there's many reasons. In forestry, one of the big reasons is we wish to use a lot of our small trees found throughout our forest in North America to improve the health of our forest. Oftentimes, these small trees are clogging up the forest, causing many disease and insect outbreak problems. If we could find markets for these small trees in biofuels or bioenergy outlets, it would greatly aid the improvement of our forest health. The second reason we're interested is to reduce the geopolitical reliance on fossil fuels and increase energy security. A third is that the use of these fuels is more carbon neutral than fossil fuels, as shown by many life cycle analyses, and it helps reduce our greenhouse gas emissions. And lastly, we want to use biofuels, produce biofuels and bioenergy to help increase rural development opportunities. Our theme is Bioenergy and Biofuels in Washington, and it's my pleasure to introduce your moderator from the University of Washington College of Forest Resources, Professor Kevin Hodson. Kevin?
Thank you very much, Bruce, and welcome to all of you today to this Denman Forestry Issue Series. It's my pleasure again to be your moderator today. Our first session is entitled An Overview of Bioenergy and Biofuels Production. And our first speaker is Professor Rick Gustafson, is in my home department, paper science and engineering, and a chemical engineer like myself. Rick his interests have been in the pulp and paper side of things, in process simulation and process control. He's done some very landmark development in single fiber analysis in pulp fibers, and he's going to give us the first talk today, which will be entitled Biofuels Basic.
Well, thank you, Kevin, and it's a pleasure to be here. I'm going to give sort of a lecture on the basics of biofuels, try to cover a very complex subject. Bruce mentioned some motivations for biofuels, and I'll just expand on that a little bit. The first one is that oil is expensive. I mean, it's up approaching $100 a barrel. At this price, we're looking for cheaper alternatives, and it motivates us to get into the business of producing fuels in other fashion. National security is an issue. We'd like to import a lot less oil, and by developing a domestic biofuels industry, that's one way that we can accomplish that. A very significant motivation for biofuels is to reduce the carbon dioxide emissions, climate change. The plot here shows the rise in global temperatures, which is now perceived by most to be driven largely by burning fossil fuels and carbon dioxide emissions. Biofuels, as opposed to fossil fuels, have the potential anyway to be carbon neutral, as this drawing shows. We can grow trees or crops. They sequester carbon as they grow, and we utilize those materials for fuels and chemicals. Combustion will release carbon dioxide. The plants capture that, and when you harvest it again, you're just recycling the carbon through this closed system. As opposed to fossil fuels, where it's a one-way street from the ground through the power plant and up into the atmosphere. Okay, so currently, there's three major ways that biofuels are produced. Ethanol can be produced from sugarcane. This is done primarily in Brazil. Ethanol can be produced from corn, and that's in the United States. And the U.S. produces a little bit more ethanol than the Brazilians do, but they're pretty close. We produce about 6 billion gallons a year, and in Brazil it's somewhere between 4 and 5 billion gallons a year. And then the other commercial way of producing biofuels is to make biodiesel from oils. This is a canola here, a very nice looking plant, but it can be produced from soybeans and also from palm oil. And in that process, we react the vegetable oil with methanol or ethanol with alkali as a catalyst, and then you get a diesel substitute and then glycerin as a byproduct, which they're currently using for a fuel. Now, let's take a look at one of these processes in a little detail here and to get an idea of what the sort of positive and negatives about it, and that's the production of ethanol from corn. So the benefits of this are it's a domestic supply, so it takes care of the importation concern, and it's relatively cheap to get into the business, and the production costs are pretty low. And this is why you see these ethanol plants springing up all over the Midwest. This is shown here is results of a study done by NREL, the National Renewable Energy Lab, where they looked at a 50 million gallon per year cornstarch ethanol plant. And the installed capital cost for this was only $48 million. Now, $48 million is a lot of money, but when I talk about cellulosic ethanol later on, keep that $50 million in mind to build a 50 million gallon per year plant. The annual production cost is here estimated at 96 cents a gallon, and that's lower than it probably is now. This is a 2002 study, and right now it's probably $1.10 or $1.20 per gallon. But ethanol from corn has its downside. One is a limited supply. Currently, we produce 6 billion gallons a year, and the estimates are that we might be able to double that, but not too much beyond that. And it competes with food. Recently, Mexico was very upset with the United States because they perceived a large increase in the price of their tortillas due to corn going to ethanol instead of food. Perhaps the biggest drawback of ethanol from corn is that it really doesn't offset that much fossil fuel. Shown here is a graph from a recent National Geographic article that compares the energy balance of producing of corn ethanol. And on the right is the amount of energy that we obtained from the ethanol, which would be 1.3 whatever units, and then the circle on the left is the amount of energy, fossil fuel energy that went into making that ethanol. So the point here is that we get very little net energy out of the system that doesn't come from fossil fuels. So from a carbon emissions point of view, this isn't going to buy us much. Okay, so if you read the National Geographic article and every other article in this field, they talk about biodiesel and corn. And then they say, well, the future is cellulosic biofuels. And so I thought I'd spend a little time about why that's the future and then why that future hasn't happened today. So there's two things that are great about the cellulosic root. One is trees are full of sugars. Roughly half of the tree is cellulose, and that's just a bunch of glucose molecules stuck end to end. About a quarter of the tree is stuff called hemicellulose, and that's a bunch of sugars, kind of different sugars stuck to each other. And then a quarter of it is lignin, which is this nature's glue that kind of holds the whole thing together. So 75% of a tree or 75% of wheat straw or corn stover is sugar, which if we could get it, would be easily to ferment and make ethanol or convert to some other fuel. So the biomass has a good composition, and there's lots of it. This is a result from a USDA study, and it projects for, I think, 2030 that we're going to have roughly 1 billion tons a year of biomass available for bioenergy production. And if you use sort of a typical number of 80 gallons per ton of biomass, we could be producing 80 billion gallons a year from this biomass. So there's lots of it, and it's got a good composition. And it doesn't suffer from the drawback of the corn ethanol, in that if we use cellulosic ethanol or cellulosic biofuels in general, we'd get good displacement of fossil fuels. In this plot here, it suggests that the energy output from the biofuels would be from twice to 36 times the fossil fuel requirement to make that fuel. So a large use of these biofuels would mean you'd have substantially lower greenhouse gas emissions. So it's all looking terrific at this point. So what's the problem? And basically the problem is Mother Nature here, and that's because as opposed to a corn, here the cellulose is really locked up tight. It forms a crystal. Those crystals are wrapped with hemicellulose, and that's all wrapped within the lignin. So this makes it very hard for insects, fungi, or us to get at it. But it's what makes wood a good building material. Okay, so how do we get at this recalcitrant cellulose and try to make fuels and chemicals from it? And basically there's three sort of main routes to do that. One is you can gasify it, and in this case you produce a syngas product. And once you have syngas, this is really useful stuff. You can make lots of different things from it by designing the proper catalyst. In this article, he talks about making Fischer-Tropsch fuel, which is kind of a gasoline sort of thing, and or methanol. But there's a company that's just building a commercial plant in Georgia, Rain Fuels, that will use this synthesis method to produce ethanol. The second way you can do it is you can change the conditions of how you heat it up a little bit, take away the oxygen, adjust the temperature, and you can make what's called bio-oil. This is a complex mixture, a dog's dinner, if you will, of stuff that comes off of the pyrolysis unit. It can be burnt itself, but it's not a particularly good fuel. But it can be refined into liquid fuels that could be used for several purposes. And then finally, you can hydrolyze the biomass, break it all the way down to sugars. And then once you have sugars, you can either ferment it to make ethanol, just like the corn to ethanol people do, or you can do run it over catalyst, dehydration, so take off the water, and then you can get aromatic hydrocarbons, and these can be used in gasoline. Now, it's this recalcitrance of the conversion of the cellulosic biomass that makes the economics of this process a little bit different than the corn to ethanol process. You need to have more robust reaction conditions, you need to have more complicated reactors, you need generally a much more involved process. So if you want to convert corn stover, that's the stalk of the corn, as opposed to the corn kernel, into ethanol, making, again, 50 million gallons a year, you need to come up with almost $200 million, not 50. And I think this barrier to getting into the business, this $200 million price tag, and this is a small plant, mind you, is a significant barrier to building these things. And the annual production cost is considerably higher. In this estimate, which I think most people would consider pretty optimistic, they think they could make ethanol for about $1.50 a gallon, which was about 50 cents more a gallon than from the corn ethanol. And again, this is from the same National Renewable Energy Lab study. So I think even though the absolute value of these numbers may not be quite right, the relative comparison of the two is pretty reasonable. Okay, so how do you make a cost-effective cellulosic biofuels? Well, these are some things, and this is sort of areas that I think need to be addressed. One is you have to have a biorefinery that can use mixed biomass sources. It's got to be able to run off the cheapest one that's most available at the present time, and that could be quite a moving target. I mean, because of international economics, you might even be importing biomass to run your biorefinery. It's got to have really good process yields. Like any chemical process, if you're not converting 90+% of whatever you're working with into a useful product, it's going to be difficult to make money. The second thing is it's got to be profitable at a modest economy of scale. And what I mean by that is we have to build a biorefinery that maybe is 100 or 200 million gallons a year, but that's going to be about it because we can't ship the biomass very far to the biorefinery. Now this is in contrast to oil refineries that are of a capacity of billions of gallons per year, a few billions of gallons per year. So this is 1/10 the size that they are. So they enjoy a huge economy of scale that we can't because of the biomass shipping problem. And then the last thing is it really needs to be able to co-produce fuels and high-value products. A mixed bag of products. So the main product would be the fuel in terms of tonnage, but the biorefinery should produce these high-value products that it can make, a substantial amount of money and improve the balance sheet of the whole venture. These high-value products could be commodity chemicals, polymers I talk about, or pulp fibers. So sort of an example of this is getting back to my roots, the pulp and paper field. And what this drawing shows is the concept of the forest biorefinery. So instead of taking wood in one end and just pulp out the other, you can see on this drawing that we're making a range of products. We're extracting hemicellulose to make chemicals and polymers. We're gasifying things to make syngas, which could be used to make fuels, generating electricity, and we're still producing pulp. So a range of products that help the bottom line of the pulp mill, or now the forest biorefinery, and make it more carbon neutral, or in fact a net sequestration of carbon. Okay, so just a take-home message here is that biofuels really have a lot of potential to be a significant portion of our renewable energy portfolio. There's a lot of it out there, and it's got the right composition to take advantage of. However, considerable work really has to be done to develop a cost-effective way of processing this material if we're going to be able to use it effectively. So, thank you.
Our next speaker is Mr. Tim Stearns, who is from the Washington Department of Community Trade and Economic Development, or CTED, as some of us know it as. He's here in Seattle. Tim is basically a business person in terms of his academic background, finance, marketing, international business, and he has been at 3 universities, Montana, Washington, and I'm sad to say Oregon, but nevertheless, he's well-traveled in academics. And Tim will be talking to us today about aligning conditions for smart biomass.
I work in trying to make businesses come together, try to take technologies that we think that we're pretty good at and take them to the world. And bioenergy is one that is kind of an opportunity that snuck up on us. And I'll tell that story a little bit further. But I would submit that the time is now, that we are really well positioned and moving forward, but we've got to move, take some aggressive steps in the near term. There are a range of things that are pushing us from really every direction, and one that I'm always keep mindful of is Washington State grows 100,000 people a year, which is 1 million in a decade, and within 50 years we're going to double, which means we have 275 people a day to feed, clothe, house, educate, employ, and transport. To fulfill their needs, I can't even imagine trying to do it without having a Columbia River again. I can't even imagine trying to double our current transportation infrastructure. So we are at really a crossroads, and I think it's a crossroads that is going to give us an opportunity that we can embrace, step up to, and take on, or it's going to pass us by. Now, what are they? I always like using an astrolabe as my navigation equipment, because it's always interesting that the center changes, that you've got a bunch of different forces, but it's pretty clear that, transportation, we were spending about $25 million a day on our economy with what we were spending on oil. Today we're spending almost $70 million a day at $90 oil. But it's also clear that that oil is going away, or it's peaking. It's getting more expensive to get to. I won't predict what peak oil is, because I don't think anybody knows, but I will predict that it's not going to get much cheaper anytime soon. We're at a crossroads in the electricity world, and I'll talk about that a little bit sooner, but in a little while. But we've clearly got to diversify. We don't have the Columbia to build on. And frankly, our lifestyle is demanding a whole different type of power than what I started my career trying to deliver. It's also clear that our ecosystems are out of whack in a lot of ways. And instead of fighting over who's going to cut the last tree, I think we've spent a decade figuring out what are the needs of those ecosystems and what can we extract and how. Now, we clearly got a lot of work to do, but I think we've come to a view that ecosystem health is pretty key, and if we just leave too much fuel piling up in the forest, it's not going to be pretty. Clearly, climate and pollution, and what I would really like to submit is the economy all around us is changing, and we just need to go and recognize what these new forces are and rethink and re-examine. It's both economic change, kind of the opportunities, but competition. I look at what we've really, it's not this simple obviously, but we've learned that everything's connected. And you know, the legislature, when they deal with people like me, it's a question of can we, should we, how, what would we do today, what would we do 10 years down the road, and finally who. I can tell you that I have gone all over the state at events where there is a new excitement that we have opportunities to really take control of our future. And one of the fascinating things in a project I coordinate on plug-in hybrid electricity, I can't imagine 5 years ago that Washingtonians would have even ventured the notion that we had even an opinion on cars, let alone how they'd operate, how they'd hook into the grid, what's the future of vehicles, can we build them with composites? And what's really exciting is you got a lot of places in Washington that really, I think, were economic takers. They kind of let others dictate what their choices and alternatives were. And I see that spirit transforming remarkably, and biofuels was one of the really cutting edge things in that regard. I try to always remind people that how simple this is, that it's going to be really easy to put together. And frankly, I don't think anybody really believed it is, but it's fairly clear that we need to engage the public in kind of a wider range of choices. And those choices, you know, we have to use the planning word, you know, mass transit and how to deal with it. How we be multimodal, how do we bike and get a car when we need to and use the bus when we can, but how do we really make this a seamless system? And really, improved vehicles is an opportunity with plug-in hybrids and biofuels, better fuels, but really pricing is imperative in the whole discussion. And I would submit we're going to end up paying for transportation one way or another, whether it's sales tax, property taxes, income taxes, fuel taxes. But one thing that's pretty clear is the way we currently spend money on transportation, it doesn't really affect our behavior very well. It doesn't get us to utilize our assets particularly well. So we're going to really need to think about that, but more importantly, we're going to have that conversation. So where do you start it? Well, I will say that biofuels has been a great place to start it, in that having done work on both sides of the mountains for a long time, it is really the first conversation we've had for a long time where urban and rural Washington saw an alignment of interests, both economic and social. Let me just give you a couple of facts. From my perspective, it's pretty clear we use a lot. The world is using a lot more. It's unconscionable and amazing to me that we as a country use 3 gallons a day. Whereas many other places use next to nothing. But really the scary thing to me is, A, it's all imported. B, its demand continues to go up. We did have a modest leveling off for a while, but frankly Americans are back to driving again, simply because we don't have particularly better opportunities or alternatives. And I think that's really the purpose of today's talk, is that we need help. And frankly, our universities, I'm really excited to see our 2 research universities, but it goes much deeper than that. Academia has really gone and recognized this is a near-term problem and a near-term opportunity. I would say that we are taking advantage of kind of the brain power and the intellectual or measured approach to problem solving from universities in a way that I haven't seen in a long time. And it's really exciting. I deal a lot with the Midwest states as we're a state that has decided to use biofuels quite a bit more in the last decade. But really, we were just buyers of ethanol to control octane, ethanol to replace MTBE. But today, we're talking about how do we produce our own. And what's really fascinating is when we originally were having the conversation, they were really threatened, that corn and soybeans are king, and the idea that we would even think of growing other crops or that we would make our own really bugged them initially. What's interesting, though, is as we have been building our industry, they recognize that they're providing us feedstock. They also recognize that what they're using for ethanol has a pretty bad energy balance, doesn't have the carbon attributes we want. So right now, universities around the country are all vying to really see what are the intellectual centers of it. And the Department of Energy and Department of Agriculture, in their wisdom, anointed a couple of places, and we weren't amongst them. What's impressive, though, is when we get around with the states, I can demonstrate how many public-private partnerships we have in a multitude of places around Washington, and how many different departments are getting engaged, from chemistry to mechanical engineering to forestry to all of those ag departments at WSU that I'll never keep straight. Let me suggest two things. I know we're generally talking about biofuels today, but it's really broader than that, because we have painfully learned that we can't just make it on fuel. You've got to make it on capturing the heat. You've got to make it on making high-value other products. And you look at those high-value other products. Sweden, for instance, does not allow you to use regular petroleum oil in chainsaws anymore. Their forest resources are so valuable that they would prefer that you use a biodegradable lubricant. Can we do that? But really the key is the whole package. But let me also describe a little bit that this is kind of creating a little bit of a revolution in government too. And it's a revolution that, we are big market participants and we are market framers. But it's also clear that if we don't have our policy, our incentives, and our regulation going in the same direction, we're not really going to get where we want to get to. Let me draw the parallel to the electric utility industry, which I also work in with a lot. Today, it's largely a large-scale, centralized, sequential system, and it's moving to a much smaller, local, distributed, interactive system. And it's basically transforming the electric energy system into the internet, an interactive and self-healing system like that. What's fascinating is the electric utility industry is really about the last big industry to go through this digitization. The oddity is digitization could not have happened without the electric utility industry. I think we're doing that same rethinking with the way we manage forests and the way we manage our agricultural areas. That we're recognizing that we can torture the energy and byproducts out of all of these different plants with a combination of heat, pressure, catalysts, decomposition, chemical mixtures. But frankly, we need a clear academic or rigorous path to get us through that. One of the things that is fascinating to me about the ethanol mistake, and that's really what I believe it to be, is that we spent 20 years creating a fuel that wasn't very efficient, and it really didn't have a very good use until we discovered that the replacement for lead was persistent in groundwater. Ethanol was a good replacement, but today We're now as states and the federal government talking about changing the currency, changing the way we keep score. We're going to change it to something that is closer to what's most sustainable, what has the right carbon footprint, what is the fuel or fuel combinations that will get us the best energy balance. One of the fascinating things about entering the notion of building a new industry is, where do you start? You don't have the luxury to just go and say, all you farmers and foresters, you guys grow us a bunch of poplars and a lot of canola and mustard, and when you have that supply, then we'll go and figure out a place that we'll crush it and refine it, and then we'll build stations. Well, you just don't get to do it that way. You build a new industry by somebody leading, somebody taking some risk, somebody listening to that cry of people that we want to do something different. I put this slide up mostly because this is really the typical business plan process that I work with all the time, and it's never this elegant or never this simple. But what's clear about it is it's a process that gets people to think. It's a process that government can work with. And what's really inspiring about Washington right now is we have the public sector, the university sector, and the private sector all rowing the boat in the same direction. So I'm going to close with a description of what Washington State's trying to do. Is we're trying to have a framework that this industry can grow and thrive in. We're going to have a clear permitting path. We are going to be huge users. We're going to be at 20% by next year. By 2015, every public vehicle is going to be either a plug-in hybrid or using biofuels. We're going to speak with one voice across state government. But one of the things that's humbling, even though I am an empowered bureaucrat, I can't control big ag, I can't control big oil, I don't even want to try to control farmers, and entrepreneurs and the next generation aren't going to listen to us anyway, so it's a huge asset. But really, we can structure this market to expand. Now, all I really want to point out with this look is the building blocks that will get us to that sustainable and innovative economy. And you really should read it from bottom to top, because you won't get to the upper reaches unless you move that. So unless you build all those building blocks. So we're going to need to converge and really leave people with choices and options. Now, we can lead individually. And it makes no sense to deny where we are, but really to embrace the future. And so I'm going to close with one final slide, and that is the change is going to lead us to challenges, but it's this huge opportunity. And the state very much recognizes the value, but we know that innovation from academia is essential. It's going to need to happen on both the fundamental and basic research side, but more importantly, it's going to need to churn out that next stage of entrepreneurs and a workforce that is adaptable to these changing opportunities. Thank you, and I look forward to making this industry happen.
Our next speaker is another University of Washington faculty member. Professor Joyce Cooper is Associate Professor in the Department of Mechanical Engineering. She has a PhD from Duke University and has a research interests largely revolve around life cycle analysis and environmental performance measurement. And she will give us a talk today which is entitled Life Cycle Assessment and Bioenergy.
Life cycle assessment is thinking very, very broadly, thinking about the system, thinking about the forestry operations, the processing of the wood, the converting of the wood to energy, and then the use of that energy, so that we have a very large systems picture of what the carbon is doing, what the energy is doing. And actually, we've been getting a lot of notice lately in bioenergy and biofuels. And this is really, really exciting for all of us that are in the United States and throughout the world involved in life cycle assessment. One of the reasons that folks have been more interested in life cycle assessment is that it's one way that can help us identify consequences of our system that we might not really think about if we were only looking at the small box that we often live in. So as a mechanical engineer, sometimes I live in a box related to how do I design a better fuel cell? And if I don't think about where the fuel comes from, I'm not necessarily understanding all of the consequences of the decisions that I'm making as an engineer of that fuel cell. Well, some historic unintended consequences are something that you guys are probably pretty familiar with. One example is the addition of lead to gasoline. Somebody somewhere thought it would be a really, really good idea to add lead to gasoline so that it would reduce the knock in the engines as the engines were operating. But they didn't think that, hey, the lead was going to go somewhere, and that all of a sudden they're going to look around the country and got kind of lead in our blood. That's kind of a drag. So, but my students, I'm excited to hear. Sometimes I ask them, I say, well, did you notice that the gas pumps, they say unleaded? Well, when was the gas leaded? And they're kind of young, so they don't remember some of these things that are going on. But just in case you were worried that we learned from the leaded gas experience, more recently, and some of my students do remember this, we decided that it would be a good idea to add MTBE as an oxygenate to gasoline, and then that would help reduce the carbon monoxide emissions coming out of our tailpipes. And that sounded like a really good idea, and so they thought they'd try it out. And they tried it out in Denver, and they tried it out in some cities in the Northeast. And lo and behold, what they found is that when they added the oxygenate to the gasoline, it actually made the gasoline a little bit more mobile than it used to be, especially when they stored it in underground storage tanks. So what happened was, it creeped out of the underground storage tanks, creeped into the groundwater, and all of a sudden, instead of having carbon monoxide emissions coming out of our tailpipe, we were blessed with MTBE in our drinking water. And so what people are trying to do at some level is step back and say, let's take a systems view of some of the things that we're doing. And within the context of bioenergy and biofuels, we have so much opportunity to build a whole new infrastructure. And as engineers, it's very, very exciting for us to think about it as, well, if we're going to build it, let's build it really good. Let's take a lot of thought and think very broadly about all of the different ways that we could make this system so that we make it the best system that it can be. And we're not going to catch everything. That's just not going to happen. But what life cycle assessment is trying to do is it's trying to help you develop a way to see if you can understand a broader set of impacts. Well, there's some other issues that have come out of life cycle kinds of thinking related to bioenergy and biofuels, and it's starting to create some lingo in all sorts of folks related to bioenergy and biofuels. You're hearing people talk about energy independence, energy balance. Does it take more or less energy to make the fuel than the fuel is actually going to provide for us? A lot of people are talking about carbon neutrality. A lot of people are talking about how far you have to transport the biomass before that system is actually a system that seemed like it would pay. And life cycle assessment is having a growing role in understanding and planning for a lot of these things. So again, when we think about life cycle assessment, we think about materials acquisition. So we're talking about the farm as a point of creation of the biomass. We're talking about forests and going into the forests and taking out just trimmings or substantial amounts of biomass from a certain stand. But we can also get biomass from waste products. And so that acquisition is more of taking it out of a process where it might have otherwise been put into a landfill or underburned or something of that sort. We think also about materials processing and engineering our processes to the biomass and to the situation at hand, and also keying the processing for how that fuel is going to be used. What if we pelletize some of our biomass? It takes a lot of energy, but it also reduces some of the sulfur, or it can. And so that can have downstream implications related to sulfur emissions when those pellets are used. So I like that idea. It was something that Rick and I had talked about. We think about materials transport, and we think about fuel use, and we think about truck emissions when we're moving biomass around. And when we're moving biomass around, a lot of it's got a lot of water in it. So we're kind of moving water around. And we also think about energy conversion and how well different kinds of biomass perform on, within the context of whether you're going to make it into electricity, whether you're going to make it into a mobile fuel, what are you going to do with it? And that sort of life cycle is really dissipative. You don't necessarily see it cycling around. But we also consider in life cycle assessment how we're going to build the infrastructure, how we're going to build the power plants, how are we going to build the hydrogen infrastructure associated with delivering those fuels to different places. And when you think about that, we can also think about how you're going to make the equipment, how you're going to optimize the equipment, how you're going to dispose of the equipment after people are finished with it. And so that really creates a cycle as well within the context of life cycle assessment. And we also think a lot about growing trees. And I'm gonna touch a little bit on growing trees, but I want to ask, growing trees and carbon is a really complicated topic. And I don't necessarily think a mechanical engineer is the best person to be estimating how much carbon is taken up by a growing tree. But I like thinking about that because that makes me know that I got to go find somebody that's better at that than I am and work with them so that when we're looking at this whole system, we can come up with something using all of our individual expertise to come up with solutions that nobody else ever thought of. So I'm not alone. There's lots of people in the United States and throughout the world that are working on life cycle assessment methodology and life cycle assessment data. In fact, the protocol has been standardized by the International Standards Organization, the ISO, and mostly it's been focusing on the estimation of environmental impacts, but also can really have a sustainability sort of edge to it. We're talking about taking a broad view of a system, and therefore we can look at not only environmental, but also it can reveal economic aspects and social indicators. But again, I'm going to argue, mechanical engineer, lots of people know about social indicators. So let's get them involved as well. So a lot of opportunity to get folks together to really understand the life cycle impacts. Well, what does life cycle assessment measure? A lot of times, again, focusing on environmental impacts, we're talking about contribution to climate change. We're talking about acidification, particulate emissions throughout the life cycle. So farming equipment, application of pesticides, application of fertilizer. We're talking about truck emissions. We're talking about fuel use by the trucks. We're talking about fuel use by the harvest equipment. And we're talking about fuel use and emissions by any conversion technologies. But we can also think about business impacts as far as materials management and business interruption. We're not really wanting to turn on and off some of our conversion technologies. And as Rick had mentioned, we want to maybe focus on a search for fuel flexible technologies because the biomass coming out of the forest isn't necessarily coming out, or it isn't coming out all year long. So if we're looking at technologies that give us an opportunity to use different kinds of biomass, perhaps that gives us more flexibility in our overall system. So social impacts too. Yeah, we can create jobs, and we can create really good jobs if we think very broadly about all sorts of engineering, business, social aspects, and see what kinds of opportunities this can have for people in the state, in Washington State. Now, I got to be honest with you. Relatively speaking, life cycle assessment's pretty new. In fact, we've had our problems, sort of growth problems, as we've started up developing ourselves as a methodology. But the ISO standardization has had a lot of influence in helping our problems. And by problems, some of what I mean is that there were some issues that were unresolved methodologically and some data that maybe didn't benefit from a large amount of review before people put it forth and it made the front page of the news. And that's hard for a group of researchers who really want to communicate important opportunities, especially within emerging systems. And what I'm arguing is that that's changed, that people saw that life cycle assessment was going to be very, very prominent in a lot of different kinds of decision making. So we needed to make sure that there were very, very well and transparent computational methods and data that people could really look at so that we could be making good, important engineering and public policy decisions. So today, if you do a search on biomass, bioenergy, biofuels, and life cycle assessment, you're going to find a lot, I'm excited to say. And what that does is it really raises the role at this point in time of summaries of bioenergy and biomass studies. And what people are doing in summaries is that they're taking LCAs from all different researchers and putting them together in a way that they can compare the results to see where people agree and where people disagree. Because think about it for a second. I'm talking about not only how we're converting the fuel, but where the fuel came from and the equipment that's used. So does that mean that I'm going to include the tires on the fellabuncher in the forest? I mean, that's a lot of modeling. And so where do we set our boundaries? And how do we make sure that we're communicating our results in a way that allow people to use those results and make good decisions from them? So this is actually from a researcher at Princeton who found a wide variation in the results related to biomass and bioenergy LCAs. But this report is a very good one because it does summarize a very large number of LCAs and tries to see where, even though people had methodological and data differences, where conclusions might be drawn. Now, one of the things that's really complicated about life cycle assessments is what we call the co-product issue. Turns out that forests produce a lot of different services, and so do agricultural systems. And for example, if we're talking about a forest can produce not only saw logs, but also chips that can be, biomass that can be used for energy production. So how do you decide what emissions for harvest are going to go with the saw logs and what emissions for harvest are going to go with what you've taken out to make into electricity? This also gets into what we're avoiding. So when I'm making electricity out of biomass, am I avoiding the grid or am I avoiding a specific technology that's on the margin that would increase with an increased demand from the grid? And these are all really key questions to look for when you're reading LCAs and interpreting LCA literature in how that's going to apply to your system. So I've had the good fortune to work with folks in California on reducing wildfire risk in California forests. Okay, now everyone in this room should say, Joyce, you should hurry up because they got some problems going on there. And we're working on this, and it's been really interesting to work with the folks there, the forestry folks and the engineers, to try and come up with some answers on if you're going to use biomass removed from the forests to hopefully return the forests to a more healthy burn pattern. Should you and how should you create energy from those systems? What we end up with is a system that produces two things. We have a system that produces electricity, and we want to compare that system to other ways to produce electricity. So we could run a diesel generator, we could run a natural gas power plant. But we can also compare that to a system that, we can also think about that as not only a system that produces electricity, but also a system that produces remediated landscape. And the question that came up in the California project was that when we go in and we treat a landscape, do we actually get the benefit of improvement of the whole landscape when we only go in and take out biomass from certain parts of it? Well, you know, from a carbon standpoint, boy, it looks really good when you think, or you suppose that you're going to make basically you're going to improve a very large landscape by only treating part of that landscape. There's absolutely, when you think about it that way, there are numbers basically say that there's nothing better than doing this. So what you're going to see as we're moving forward is a lot of, I think, focus on the use of residuals as a way to produce electricity and to produce biofuels, because it's those materials that we would be otherwise throwing away. But the assumptions related to how much carbon you're sequestering are all over the board. So what I have here is essentially the contribution to climate change related to different treatment options in California forests, from not treating at all, so accounting for the wildfires that occur when we don't treat at all the way through very, very aggressive treatment on public and private lands. And what am I going to compare it to? Should I compare it to the grid? Should I compare it to a natural gas power plant? People don't agree. So what I do is I do it all so that people can see how that affects the results. We're at a really, really good point in life cycle assessment, because there's a lot of people interested in how developing life cycle assessment can actually help you better understand opportunities to move forward. And for example, here, what we have is we have the ability to look at what within the system consumes the most energy, produces the most particulate matter, produces the greatest amount of emissions for climate change. What this tells me is that I can look at power plant technology and I can try and improve it, and I should be able to have substantial improvements on the life cycle in general. So the take-home messages here are, you're going to see more about life cycle assessment, that there's absolutely opportunity for all different kinds of disciplines to be brought to bear in understanding all of the different aspects of bioenergy and biofuels life cycle. And it's not only that they can, but it's really that they should, because we all bring a wonderful set of expertise, but when we work together on projects like this, we can really go forth and create much more understanding of the system in general and greater opportunities for us here in the state of Washington and beyond. Thank you.